Today we're going to talk about how to integrate rational functions using the partial fraction decomposition method. So let's get right into it. Let's find the indefinite integral of x minus 9 divided by x squared plus 3x minus 10. So what's the basic idea behind partial fraction decomposition? Well, let's say if you want to add two fractions. Let's say 1 over 5 plus 3 over 4. In order to add these two fractions, we need to get common denominators. So I'm going to multiply the first fraction by 4 over 4 and the second one by 5 over 5. 4 times 5 is 20, 4 times 1 is 4, 3 times 5 is 15. So this is equal to 19 over 20. So that's what you need to do if you wish to combine two single fractions into a larger fraction. Partial fraction decomposition is the reverse of combining two fractions into a single fraction. It takes one large fraction and breaks it down into the two smaller fractions. And that's what we need to do. We need to take this fraction, break it down into two smaller fractions, and then integrate those two smaller fractions. So how can we do that? Well, the first thing is we need to make sure that the denominator is completely factored. So we need to find two numbers that multiply to negative 10 but add to 3. So what are those two numbers? It's going to be positive 5 and negative 2. They add up to 3 but multiply to negative 10. So what we now have is x minus 9 divided by x plus 5 times x minus 2. X plus 5 is a linear factor, and x minus 2 is another linear factor. When you're dealing with linear factors, you're going to use one constant in a numerator, like a or b. So we're going to break this fraction into a over x plus 5 plus b divided by x minus 2. So linear factors include like x, 3x plus 8, x minus 4, even x minus 3 squared. That's a repeated linear factor. So anytime you have a linear factor, you're only going to have one constant in the numerator. Now if you have a quadratic factor, like x squared plus 4, or x squared minus 2x plus 5, then in a numerator, instead of a single constant b, you're going to have something like bx plus c, or dx plus e, when you're dealing with quadratic factors. Now what we need to do is we need to determine the value of a and b. So right now let's ignore the integral sign. So let's get rid of this. We can get back to it later. How can we determine the value of a and b? What we need to do is multiply both sides by this denominator. So we're going to multiply both sides by x plus 5 and x minus 2. Now, if we take this fraction and multiply it by those two factors, these will cancel. So on the left, we're going to be left with x minus 9. Now, if we take this fraction, multiply by x plus 5 times x minus 2, the x plus 5 factors will cancel. And so it's going to be a times x minus 2. Now, if we multiply these two, the x minus 2 factors will cancel, and we will be left with b times x plus 5. Now, in this form, you can plug in an x value to solve for a or b. I'm going to plug in 2. When x is 2, on the left it's going to be 2 minus 9. On the right, 2 minus 2 is 0, which is great. So that gets rid of a. And so I'm left with one variable, b. And 2 plus 5 is 7. Now 2 minus 9 is negative 7, and that's equal to 7b. Dividing both sides by 7, I can see that b is equal to negative 1. So now let's calculate a. This time I'm going to replace x with negative 5. So negative 5 plus 5 will be 0. This is going to be negative 5 minus 9, and that's equal to a times negative 5 minus 2. Negative 5 minus 9 is negative 14. Negative 5 minus 2 is negative 7. And negative 14 divided by negative 7 is positive 2. And so a is 2. The expression that we had before was a over x plus 5 plus b over x minus 2. So now we can replace a with 2, and we can replace b with negative 1. Now what is the antiderivative of 2 divided by x plus 5? Now let's go over a few things that you need to know. The antiderivative of 1 over x is ln x plus some constant c. The antiderivative of 1 over x plus 4, if you just have a linear factor, it's going to be ln x plus 4, and then plus c. So if you integrate, let's say, 1 over 3x plus 4, it's going to be ln 3x plus 4, but if you use u substitution, you'll find that it's going to be 1/3 ln 3x plus 4. So if this is a linear factor, and if you take the derivative of 3x plus 4, which is a constant, that's going to give you 3. And you need to divide this by 3. So let me just give you a few more examples. So let's say if we want to integrate 1 over 5x minus 2 and 4 over 7x minus 3. So for the first one, it's going to be the natural log of 5x minus 2 times 1/5, because the derivative of this is 5, and you have to divide the natural log expression by 5, and then plus c. Now for the next one, it's going to be the natural log of 7x minus 3 divided by 7, but we have a 4 in front, so it's going to be 4/7 times ln 7x minus 3 plus c. Now let's work on the rest of the problem. Let's finish this part. So the integral of 2 over x plus 5 is going to be 2 times the natural log of x plus 5, and the antiderivative of 1 over x minus 2 is going to be natural log x minus 2, and then plus c. And so this is the final answer for this problem. So that's how you can use partial fraction decomposition to integrate rational functions. Now let's work on another example. Integrate x squared minus 1 divided by x cubed plus x dx. So first, we need to make sure that the denominator of this fraction is completely factored. So we can begin by taking the GCF out. So the greatest common factor is x, and then we're left with x squared plus 1. So x is a linear factor. X squared plus 1 is a quadratic factor. So now let's ignore the integral sign for now. So we could break down this fraction into a divided by x plus bx plus c, since we have a quadratic factor, over x squared plus 1. Now just like before, let's multiply everything by this denominator. So by x times x squared plus 1. So if we multiply this term by these two factors, this will completely cancel, leaving behind the numerator of x squared minus 1. And if we multiply a over x times this, the x variables will cancel, leaving behind a times x squared plus 1. And then if we multiply this fraction by these two factors, the x squared plus 1 factor will cancel, we're going to have bx plus c times x. Now, what values for x should we plug in? If we plug in 0, this entire term will equal 0. And so we're going to have just one variable, a. So let's try that. So when x is 0, x squared minus 1 will be just negative 1. And then we're going to have a 0 squared plus 1, which is just 1. And then this will just completely disappear. That's just going to be 0. So we can see that negative 1 is equal to a. So I'm going to write that on the side here somewhere. So now we need to calculate b and c. So what should we do at this point? Now, there's no other number that we can plug in that will just get rid of b or c. So therefore, we're going to have to do this another way. Let's organize the terms that we have. On the left, we have x squared minus 1. On the right, it's going to be ax squared plus a. And then if we distribute x, it's going to be bx squared plus cx. So let's group together the x squared terms. So this is going to be x squared minus 1. And then if we take out x squared, it's going to be a plus b times x squared if we factor out x squared from these two terms. Now the next term that we need to write is going to be c times x. And then we're left with the constants. So we could set one x squared equal to a plus b times x squared. Because they both carry the same variable, x squared, that means that 1 has to equal a plus b. And then we can see that negative 1 has to be equal to a, which we have that here. Now, there's no x variable on the left side. We have x squared, but not the x term. So therefore, cx is equal to 0. You can rewrite x squared minus 1 as x squared plus 0x minus 1. And so you would set cx equal to 0x, which means that c is equal to 0. Now, using this equation, we could solve for b, knowing that a is negative 1. So replacing a with negative 1, we're going to have this expression. So we need to add 1 to both sides. 1 plus 1 is 2, so b is equal to 2. Now that we have the values for a, b, and c, let's continue where we left off. So that integral is going to be a divided by x plus bx plus c over x squared plus 1. So now we can replace the constants. So a is negative 1, and b is 2, and c is 0. So it's just going to be 2x divided by x squared plus 1. And now what I'm going to do is separate this into two integrals. So the first one is going to be 2x divided by x squared plus 1. And for the second one, it's going to be negative integral of 1 over x dx, which we know the answer for. Now the first one, we need to use u substitution. Let's set u equal to x squared plus 1, so that du is going to be 2x dx. And if we divide both sides by 2x, dx is du over 2x. So the integral of 2x divided by x squared plus 1 dx, that's going to equal the integral of 2x, and then we can replace x squared plus 1 with the u variable, and then let's replace dx with du divided by 2x. So we can cancel 2x, and so we have the integral of 1 over u du, which is the natural log of u, and u is x squared plus 1, so this is going to be ln x squared plus 1. So we can replace this part with the natural log of x squared plus 1. And the integral of 1 over x, we know it's ln x, and then plus c. Now we can adjust this expression. You need to know that the natural log of a minus b is ln a over b. It's the quotient rule for logs. So we can rewrite this answer as the natural log of x squared plus 1 divided by x plus c. And so I'm going to leave the answer in this form. And so that's it for the second example. Now let's work on one more problem. Let's integrate dx divided by x to the 4 minus x squared. Go ahead and try that. So just like before, we need to take out the greatest common factor in the denominator, which is x squared. And so we're going to be left with x squared minus 1. Now we could factor x squared minus 1. Using the difference of squares technique, it's going to be x plus 1 times x minus 1. So now how many fractions are we going to get in this example? Now let's ignore the integral sign for now. Let's focus on decomposing a fraction into smaller fractions. Notice that we have a repeat linear factor. What should we do when we encounter those situations? So for this example, we're going to have a over x plus b over x squared. Now let me give you another example. Let's say if we have the fraction 4 divided by x plus 5 cubed. So we have 3 repeat linear factors. So it's going to be a over x plus 5 and then b over x plus 5 squared plus c divided by x plus 5 cubed. So hopefully you see the pattern here. That's what you need to do whenever you have repeat linear factors. Now we have 2 more linear factors that we need to account for. So this is going to be c over x plus 1 plus d divided by x minus 1. And let's multiply both sides of the equation by this denominator. So this fraction times that denominator, the denominators will cancel, and so we're only going to get a 1 on the left side. Now a over x times x squared, x plus 1, x minus 1. A next variable will cancel, and we're going to have a times an x left over times, I'm going to write x plus 1 times x minus 1 as x squared minus 1, just to conserve some space. Now, if we multiply b over x squared by this denominator, what will we get? What's going to be the result? The x squared terms will cancel, and so it's going to be b times x plus 1 times x minus 1, or simply b times x squared minus 1. Next, let's multiply c over x plus 1 by this denominator. If we do that, the x plus 1 terms will cancel, and so what we have left over is going to be c times x squared times x minus 1. And then for the last one, the x minus 1 terms will cancel, and so we're going to be left with d times x squared times x plus 1. So let's see what we can do here. If we plug in 1 into x squared minus 1 will be 0, and x minus 1 will be 0. So on the left, we're going to have 1, and all we're going to have on the right side is that expression. So it's going to be d times 1 squared times 1 plus 1. 1 plus 1 is 2, so we're going to have d times 2, or 2d. And dividing both sides by 2, we can see that d is 1/2. Now, what's the next best number to plug in into x? What do you recommend? I recommend 0 because if we do that, a times 0 is 0, c times 0 squared is 0, and d times 0 squared is 0. So we're going to have left over 1 is equal to b times 0 squared minus 1. 0 squared minus 1 is just negative 1, and 1 divided by negative 1 is negative 1. So b is negative 1 in this problem. So now we need to calculate a and c. So it turns out that we're going to have to group this in such a way to write a system of equations. So let's go ahead and do that. Let's distribute ax to x squared minus 1. So it's going to be a x to the third minus ax. And then if we distribute b, we're going to have bx squared minus b. Doing the same thing for that, it's going to be cx to the third power minus cx squared. And then we're going to have dx cubed plus dx squared. So we have a cubic polynomial on the right. So on the left, it's going to be 0x cubed plus 0x squared plus 0x plus 1. This whole thing is equal to 1. Now let's group every term that has an x cubed. So it's going to be a plus c plus d times x cubed. Now for the x squared terms, we have these three. So that's going to be plus b plus d minus c times x squared. And then there's only one term that has an x. So it's going to be minus a times x. And then for the last one, this is the only constant. So minus b. So let's start with the constants. We can see that the constant 1 on the left is equal to negative b, and thus we get b is negative 1. Now we can see that 0x is equal to negative a times x. So we can say that a is equal to 0. So that's a new answer. Now the last thing we need to do is calculate c. So let's set 0x cubed equal to a plus c plus dx cubed. So the x cubes will cancel, and 0 is equal to a plus c plus d. Now we know that a is 0, and d is 1/2. Subtracting both sides by 1/2, we can see that c is going to be minus 1/2. So previously we had the expression a over x plus b over x squared plus c over, I believe that was x plus 1, and then d over x minus 1. A is 0, so 0 over x, that's just going to disappear. B is negative 1, so we're going to have negative 1 over x squared, and c is negative 1/2. So that's going to be minus 1 on top, and then 2 times x plus 1. And then d is 1/2, so that's going to be plus 1 divided by 2 times x minus 1. Or if you prefer, you could see it this way. So for C, that's going to be negative 1/2, and then times 1 over x plus 1. And then for D, plus 1/2 times 1 over x minus 1. It might be better to write it this way, especially when you're integrating this expression. Let's start with the antiderivative of negative 1 over x squared. So first, we need to rewrite that expression as negative x to the minus 2. And then we could use the power rule. Negative 2 plus 1 is negative 1, divided by negative 1. And so these two negative signs become positive. And then if we move the x variable back to the bottom, this becomes 1 over x. So the answer now is 1 over x, and the integral of 1 over x plus 1, that's going to be the natural log of x plus 1, and there's a constant in front of it, negative 1/2. And that's why I chose to keep this fraction on the outside, because you can easily see that the integral of this term is just ln x plus 1. And then it's going to be plus 1/2 natural log x minus 1, and then plus c. Now, just like we did before, we can combine these two natural log expressions into a single natural log. So first, let's factor out positive 1/2. So I'm going to take it out from this one first. And so that's going to be ln x minus 1. And then if we take out 1/2 from this term, it's going to be minus ln x plus 1. Now, as we mentioned before, ln A minus ln B is ln A divided by B. So therefore, ln x minus 1 minus ln x plus 1 is going to be the natural log of x minus 1 on top and x plus 1 on the bottom. So I'm going to write the final answer like this. It's 1 over x plus 1/2 natural log x minus 1 over x plus 1 plus c.